Hello. Hello, are you able to? Okay. So hold on. তুমি আমার ক্লাসরুমে ঢুকেছো গো? আচ্ছা, so did you manage to download the material? Okay, so what I want you to do is take the time to go through it first. When I can walk you through it, which I will, but I would prefer if you go through it first and then I walk you through it so that it will be easier for you to figure out what it is all about. Okay? So what I will do is today I'll give you a very quick walkthrough. But this is not the only class that you will have. Okay, I want you to go through it, and then maybe Friday or sometime in the evening we will go through it again, so that you have by the time you have looked at all of this and you have your questions ready. এটা বুঝতে পেরেছি ওটা বুঝতে পারিনি ইত্যাদি ইত্যাদি. Okay. So what I would do is let me quickly try to hold on just a second. Okay, so let me share the screen. So can you see my screen now? So this is the classroom, and this is the first few classes. Okay, so here you go. Can you see the screen? So the important point in this class is these are just things to figure out how things are. Is the stuff about crystals. Okay. So have you been introduced to crystals before? Yes. So this is the way it is, and then this is exactly what it is. The crystal lattice. What is lattice? What is basis? Okay. So this is the description of it, and then we define. Okay. So lattice is basically okay. So let's see. An ideal crystal is constructed by infinite repetition of identical units in space. Okay. So you take a unit cell and you repeat it in all possible directions to cover the entire space. That is your lattice. Now, the lattice itself, okay, is the geometrical position, gives you the symmetry. Now, what you put at the geometrical location is the basis. So, let me give you an example. So, this is a coordinate system. So, for example, you have a unit cell here. So, this unit cell, okay, is a lattice. Now, at each position of that unit cell, at each corner, you could have a single crystal, or you could have a single atom, or you could have two atoms. So the basis is the single atom or two atoms, and the geometry, the coordinate system, is the lattice. Okay, where you put in space is the lattice. What you put in that space is the basis. So together you have a crystal. So then you have some calculations, which is easy. You can go through it and you will be able to review. I'm going through it very quickly because these are simple things. And then you have the various types of lattices depending on symmetry. So you have the cubic, the cubic. So the symmetry depends on essentially, if you look at this picture, can you see this picture? It says ABC, alpha, beta, and gamma. Okay. So depending on the ABC and the alpha, beta, gamma, the angles, then you have the various lattices. Okay. So here you go. ABC are the same. Let's look at cubic here. A1 is equal to A2 is equal to A3, which is the same as ABC, is the same. And the angles are 90. Can you see the cubic? So that is cubic. And then if the symmetry changes, then the nature of the unit cell will change. So you have tetragonal or orthorhombic, in which, for example, in orthorhombic, you have none of the ABCs are the same, but the angles are all 90. And the monoclinic, you have none of them are same, two of them are 90 and one of them is not. Okay. So depending on the symmetries, you have the various crystal types. So these are the images of the crystal types. So there is something called triclinic, monoclinic. It all depends on the ABC and the angles. Okay. And then we talk about the simple cubic, and then there is three different types of cubic system. The simple cubic, the face-centered cubic. If you look at the third picture, you have atoms both at the corners as well as in the center of the faces. And then you have that's called the face-centered cubic. And then you have something called the body-centered cubic, which is the atoms are in the corner and as well as in the center of the body. Okay. So these are the different types of cubic systems. And then we talk about silicon. Silicon is a very specific face-centered cubic system in which instead of one atom at the lattice point, you have two atoms. As I said, the basis can be, single atom, two atoms, can be a can be a molecule, does not matter. Here you have two atoms. One, if you look at this picture at the bottom, so it's a face-centered cubic system in which one is at the corner, okay, and one is along 1/4 the body's diagonal. So if you take a diagonal from one corner to another corner, draw a straight line, and you come to the 1/4 point, then you'll see one more atom there. Okay, I want you to look at this structure carefully. So can you see the structure now? So if it was a simple cubic, you'll have only atoms in the corners. If it was a face-centered cubic only, you'll have atoms at the corners and the center of faces. But this one, the silicon lattice, this is all of this discussion builds up to the fact that we are now talking about a silicon lattice. A silicon lattice has atoms both at the corner and the center of faces, but there is three more atoms inside. These are shifted 1/4 the body diagonal away. Okay, so if you take the corner at the bottom and then you go 1/4 the distance along the body diagonal, you see another atom. Okay, so that is something called a diamond lattice or the silicon lattice. They have the similar lattice actually. Okay, so this is the very specific problem of the silicon lattice. And then we talk about something called Miller indices. So the crystal planes, they have different numbers. So how do you know which plane is which? So I want you to look at the second picture at the bottom. Can you see there's something called 100? So can you see the red plane? So where does the red plane cut the x-axis? At a point, right? Some point. Where does it cut the y-axis? Nowhere. At infinity, right? It's so it's parallel. So where do parallel lines meet? At infinity. So z-axis the same. Okay. So the point is, what you need to do is take the intercepts. So let's go back to these lines. The plane intercept the axis at some numbers. Okay. And then you take the reciprocal of those numbers and then simplify them. If you do that, then you will get reciprocal of infinity is 0. Okay. So this plane is the 100 plane because it cuts the x-axis at some point. It does not cut the x and the y and the z axis. It cuts it at infinity. So you do the reverse. Do the reverse. Infinity. The reverse is 0. Yes, 1 by infinity is 0. So if you do the reverse and then you simplify, then it becomes 1, 0, and 0. So this red plane is called the 100 plane. Now you take the second cube box. Can you see the red plane here? It's a different kind of a plane now. It's like a curtain. Okay. So where does it cut the x-axis? At some point, A, let us say. Where does it cut the y-axis? A, let us assume. It's a cubic. Where does it cut the z-axis? Infinity. So you take the reverse. 1 by A, 1 by A, 0. Multiply throughout by A, you get 110. So this plane is 110. This plane is 111. Something like that. So this is how you define individual planes. And then, so this is another picture of the same story. And then there is something called the packing density. You have to figure out how many atoms are there, and how much of the space is material and how much is vacuum. Okay. So we assume atoms are hard spheres. Okay. So if you assume atoms are hard spheres, let's try to figure out. Let's see, can you see the simple cubic picture here? So can you see the atoms are touching each other, right? And they are hard spheres. And 1/8 of a whole atom is inside the cube. Okay. So how many corners are there? 8. And how many atoms then? 1/8 into 8 is 1. Okay. So what is the packing fraction? If the distance between, okay, so if the radius is r, distance between the two atoms is how much? Twice of r? 2r. Okay. So how much are we getting? What is the total volume? Is a cubed, let us assume. The blue one at the bottom. And how much of it is actually solid? Number of atoms per unit cell is 1. And then 4 by 3 pi r cubed. R is half A. So you do the math, you get 52.52. Similarly, you go to the BCC, similar kind of math, and you get another number. Here, the atoms are touching each other along the body diagonal. Can you see that? So the body diagonal is how much? Root 3a. And how many atoms are sitting? 3 of them. So from there, you do the math, and then you come up with how much is the packing fraction. So this is simple. So all of them are very, very simple things. And so that's how we end. In the final, we talk about the various kinds of semiconductors. And the most important point here is, of course, the lattice constants, which is the distance between atoms. But also, an important point is we have to define that there are different kinds of semiconductors. There's the 3-5 semiconductors, 2-6 semiconductors, etc., etc. So 3-5 is from group 3 and group 5 in the periodic table. So you have aluminum phosphide, aluminum arsenide. All of these are semiconductors. Okay. So why don't you look up the old periodic table? Okay, find the periodic table, not the new one, not the one that you are using these days, but the old one where there is absolutely. So then you will find the group threes are aluminum, gallium, indium. The group five are phosphorus, arsenic, antimony. And so you have compounds between them. Aluminum phosphide is a semiconductor, aluminum arsenide is another semiconductor, and so on and so forth. So this is just to introduce you to the fact that there are many, many different kinds of semiconductors. Okay. And then we talk about the fact that there are three types of materials, something called single crystal, which we talked about already. And then there's something called polycrystalline materials. What are polycrystalline materials? These are materials where there are small regions which are crystalline by themselves, but they are mismatched. They are not the same oriented with respect to the next region. So if you look at this third picture, can you see that there are various which we call domains or in regions, grains, and each of them are crystals, but they are misoriented with respect to each other. So these are called polycrystalline materials, formed of individual grain. Each grain is a single crystal. The single crystal misoriented with respect to each other. Grain boundaries, okay, are present between the grains. So that is what a polycrystalline material is. An amorphous material, something which does not have any periodicity whatsoever. No, this is polycrystalline. This is, yes, most materials are polycrystalline by nature. Metals are polycrystalline than ones. Single crystals are difficult to find. In nature, when they are there, it's very expensive, and you have to make them. How you make them is another subject of another class. Now, and all that. Yes. What I'm asking you to do is exactly that. Go through them, and then whenever, because these are engineering things, these are simple things. Whenever there is a problem, it's easier for me to explain to you while you have already looked at them. And that does not end this week. That can be from any time from today till the exam day. It does not matter. You don't have to finish all of them in this week. So what I do not want you to do is like assume that I will not help you out like 5 days down the road. No, I will go through the whole thing and then ask me questions. That's the best way. Rather than try to just rush through the slides and assume that you have learned everything, which makes no sense. Okay, and then the next part of the chapter is called bonds. And then there are ionic, these are basic high secondary chemistry. You know, ionic bonds formed by Coulombic attraction, the ions, right? One of the electrons shift to the other, it forms charge, positive and negative charges, then they are electrostatically attracted. So, these are the nature of the solids. Ionic solids are formed by Coulombic attraction. They have large cohesion energy, low electrical conductivity, and so on. So these are just stuff that you remember. Now, this is more important. Okay, so the question is, why do you actually form a crystal? Okay, this is something to understand. The rest is not. So, why do you actually form a crystal? Now, why do you form a crystal is very, very critical. Now, imagine you see this diagram, right? Imagine one atom is at the origin, and the second atom is at a large distance, and they are ions. And so, if they are ions, they are attracting each other. So, can you see the attractive Coulombic potential is proportional to 1 by r? That is a dotted line that goes down. Okay. Now, so they are coming together, they're coming close to each other, and then they start repelling each other. Obviously, it will not be like they will come and coalesce because nucleus will then repel. And then you have the repulsive potential. Can you see that? The one that goes up. Now, that is something called atomic force. And atomic forces obviously are very, very non Coulombic, They don't go up by 1 by r, they go up by 1 by r to the power m, so they are like short range forces. They go up very fast. Now, together, what is the potential? Is the total of the two. So the line that is not dashed, the continuous line, gives you the total potential. So at short distances, can you see it's high? And then it crosses zero, becomes negative, and then at longer distances, it asymptotically goes to zero. Now, you know from thermodynamics that a system tries to minimize its energy. So where is the minima? That point given there at U0. And what is the distance between atoms? Is R0. So essentially, if you take two atoms and you let it move freely, the minimum energy position is there at a distance R0. Now, what is the other thermodynamic story? A system always tries to minimize its energy. So, given the opportunity, atoms will always be placed at a regular periodic intervals. So, this is why crystals are formed. Yes, good question. The question is given the opportunity, do you think atoms in a solid can move? No. So, when can they move? When they are at high temperature? Now, think if you give a solid material a high temperature and a lot of time, then they will form crystals. Now think about it. Where do you find such places? High temperature and long time in nature? Absolutely. So where do you find diamonds? Right. And then it cools down very, very slowly from high temperature, which is why most of the diamonds you find are inside the kimberlites, so to speak, that is inside the volcano. That is precisely the point. Uh-huh. That's the important point. Good. So here you go, crystalline solids, and then there is covalent bonding. You know this. This is all basic chemistry. The nature of covalently bonded solids, they are formed. The localized bonds, large cohesive energies, low electrical conductivity like diamond, very low electrical conductivity. And then there is a metallic attraction. So this is a type of solid is metals. So there is a Coulombic attraction, and then these are conducting, and it absorbs light. And then there is the band theory of solids, which is there in the other part of the lecture, not mine exactly. AB Sir, I think, would teach you the band theory. So that I just put in here. Here, what is a conduction band? What is valence band? It's there. Okay, and so here, for example, we have the 3,5 semiconductors, the 2,6 semiconductors, and all of those stories. So if you can see the group 4, right? Silicon germanium is the natural semiconductor, and then you have aluminum nitride, aluminum phosphide, aluminum arsenide, aluminum antimonide, gallium nitride, etc., etc. So these are three fives, and then two sixes are zinc oxide, zinc sulfide, etc., etc. So these are also semiconductors. Can you see that? The group 4, the three fives, and the two six. Okay, so that is, and then you have this important picture where we have placed all the semiconductors on the same graph in which we talk about band gap and lattice constant. Okay, I want you to go and find out gallium arsenide. Okay, can you find indium arsenide? So the line joining these two is an alloy of the two. It is called indium gallium arsenide. INGALlium GaAs. Okay, that is the line. So these compound, no, it's there. The line represents that. The line joining gallium arsenide and indium arsenide represents that alloy. Okay. Now, what is important is let's go back to this diagram here. So this is not strictly not my class, but still it's important. So can you see that electrons and holes, conduction band and valence band, when they recombine, they give off the energy. It can be in the form of light. Okay. Now, the question is, what is the energy of the light? What is the wavelength of the light? What is the color of the light? Depends on what? Depends on the band gap. Okay. Now, here we are plotting the band gaps. Okay. Now, depending on your requirement, it is not like we can, accept any light. We might have a requirement for a light at a particular wavelength. Okay. So, how do you know which material will emit that wavelength? You know it from this diagram. What is the y-axis? It's the band gap. For example, if I want 1.5 micrometer light, which is a very, very important light for communication purpose, can you see the 1.5 in the y-axis on the other side? Now, if you draw a parallel horizontal line, can you see it will cut the line joining gallium arsenide and indium arsenide at some point? That composition is necessary to generate the light in that wavelength. This is the most important graph in the whole of semiconductors. Absolutely. And this is another version of it, a little bit more expanded, yes, in which we put the Vibjor. Okay. Now, there is one more point here. Can you see some of these lines are dashed? Now, those dashed lines are something called indirect semiconductors. They do not emit light. The continuous line are the direct bandgap semiconductors. Okay. So that is the so together this diagram is the most important diagram of all of semiconductors because you can figure out exactly what you want. Okay. So that is the band gap of. So that is the end of the first few classes that I went through it much more slowly, try to explain every step of the way. But that is precisely what it is. Okay. So what I will do is I will stop now. I'll give you some time to do other things. And then what I will do is maybe Friday we will do another section. Okay. You tell me whenever you have the time in the evenings. Is it? Saturday is oh, okay. Okay. How about Thursday then? Yeah. th- Okay. 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 So okay. Okay. What I will do is I'll make sure because what I hate is trying to give you the whole thing in one shot and assume that you will be able to keep your head for all of this. This does not make any sense. Okay. So let's. How about tomorrow? You just give. Yes, just give me a call. You just leave me a message. We will go through another section. Okay. Good. Let's do that. Like we said, like we have the semiconductor here, silicon. See, the basis, it's a FCC, face-centered cubic, but the basis is two atoms, one at where it is and one foot the body diagonal away. So that is the basis. So the base, A face centered one. Yeah. Yes. So if you look at it, see a face centered. Okay, so let me try to see. Can you see the bottom left? And then you go up, you see another one in the corner, right? And you go to the other side, you see another one in the corner. So the corners are all taken. And there is one in the face center also. But can you see there is one more atom? If you go from this left to the other corner, a little bit distance away, and you see one more atom? Now that is one foot the body diagonal along that distance. Now, if you take these two atoms together as the basis, and then place at all FCC positions, you will get the crystal. Because there are four, right? Not three. There are four. There are four. Yes, there are four. See, if you go to the other picture, let me go up here. There are four. The rest are outside the box. So that will be part of another unit cell. Okay, so here you go. So that's the whole story so far in this storyline. Okay, so tomorrow let's do the. We'll try to very quickly dust through the CVDs and this and that and the epitaxis and all of those things. Okay, but don't worry about it. We can keep going through this explanation sessions even after your internals are over. Okay, good. Thank you. Thank you. Good night.